Well, the first sort of example I'll cover is a fictitious example, and it illustrates an important pattern of pipelining. So let's say you're assembling a car, and there are 4 stages in the assembly, wherein each stage takes 2 minutes. Now, if the car is processed in serial mode, that is, serial mode means when a car comes in, no other car can be processed until the entire car comes out. And this entire pipeline takes 8 minutes, so in serial mode your throughput is 1 car every 8 minutes. Pipeline mode means is that if the first car is in the second stage and the door is getting done, the second car can come in and operate in the chassis stage. And as the pipeline moves, in the best case the pipeline is full and all 4 stages are being utilized. Even though the end-to-end time for a single car is 8 minutes, the throughput is going to be better because the utilization first stage has gone up. So what would be the throughput in this example in pipeline mode? Well, since all 4 stages can get utilized and all 4 stages have the same amount of time, the pipeline mode would process 4 cars per 8 minutes. And therefore you've got a 4-fold improvement in throughput. But unfortunately, real life is not as well balanced as this example. And what would happen if the door took 4 minutes as opposed to the other stages that take 2 minutes? Now, what would be the throughput in such a system, given that now a car takes 10 minutes to process as opposed to 8 minutes, and you've also got a lopsided pipeline? Well, sometimes the answers are easier to get when you relate things to food. So let's convert this to a food example. Let's suppose you're at a McDonald's or a Burger King and you're ordering burgers along with fries. So you would typically have a pipeline of placing the order, having the burger and getting the fries. So in serial mode, one order would take 60 seconds. But in pipeline mode, you can do 3 orders in 60 seconds. But what if there was a lopsided pipeline here and the burger processing would take 30 seconds? Well, you can see it should be quite clear that if the burger processing takes 30 seconds, that is a bottleneck. And you cannot do a burger faster than 1 every 30 seconds. So that would limit your order throughput to 1 order every 30 seconds. And you can now go back to the pipeline example of a car. And if the door takes 4 minutes, there's no way that you can get a throughput of faster than the slowest stage. That happens to be the door. So no matter how many cars you try to put on the pipeline, your slowest stage will limit overall throughput, and your throughput would be 1 car every 4 minutes, or the throughput is whatever is the slowest stage, that would limit your throughput. Now this kind of a pipeline was defined in the example of throughput. Let's take a real life example where we use the pipelining concept to improve response times. So this happened in a large stock exchange which had initially individual traders, but as time progressed, a lot of brokerages came in. And the differences between individual trader and a broker is that a broker tends to place large orders. And if you get a large order of, let's say, 5,000 or 10,000 or 20,000 of a given stock in quantity, it is going to match against a large number of small orders. And a large order is going to result in a large number of trades that is going to be bursty in nature, because quite often you will get a number of small orders and suddenly get a large order. So the burstiness is going to cause a lot of queuing in the system, and that was creating havoc in the stock exchange. So if you look at the heart of the stock exchange, it has an order execution process which goes through 5 steps. That the order gets validated, then the order is confirmed to the end user. That's what the response time really is, that I've received your order. You cannot say when your order will match versus counter orders. Then the order is written to an order book. The order is matched against, buy orders are matched against sell orders, and sell orders are matched against buy orders. And whatever trade occurs through the matching, a trade confirmation is sent. However, this processing has to be done first come first serve. And as it happened that until these 5 steps were executed, the next order could not be taken in from the queue. So what used to happen was that one large order will cause a lot of trades, and this first come first serve queue started building up. If we look at the timings, just a ballpark numbers, that the validation, let's say, takes 1 milliseconds, which is pretty fixed regardless of the size of the order. But the matching part, that is from step 3 onwards as it was defined, would take anywhere from 1 milliseconds to 50 milliseconds. There's a high amount of variability in matching depending on the order size, and this causes significant queue builds up. It's like, you've fired a request to a printer for 1 page, but somebody ahead of you has fired an entire manual for 100 pages, and you have to wait behind that person just for your 1 page. So essentially in this example, what was done was to build a simple pipeline that split the processing into a validation process and a matching process. What really matters for response time is a validation to the end user. So step 1, you validate the order. Step 2, send order confirmation. Let's say you've got an order 1, 2, 3, 4 that is confirmed. This happens pretty much in a sub millisecond. And then the balance of it can be sent to the matching queue, which can take its own sweet time relative to the 1 millisecond. Now, this is how the split is done, and this really helped improve SLAs drastically. But keeping in mind, we had this point raised that if your system is in maintenance, then make sure that there is absolutely no problem when you make a change for design. Now in this design change that is done, where validation and matching are split, you have to keep in mind that there is a bug that has been introduced. If you think about it, what can happen, let's say once order number 1, 2, 3, 4 is confirmed, that say a trader modifies the price of order number 1, 2, 3, 4. So you have an order modification. When it comes to validation, validation will first check against the order book and get the order details and then validate the order against it. But in this case, suppose there is a heavy queue buildup at matching and the user immediately went about and modified the order after confirmation. So much so that by the time the modified order was placed, the queue buildup was not taken care of in the matching stage. And as per this red circle that you can see in matching, the order has still not been cleared. Therefore, if step number 3, which is writing the order to the order book, has not been done, and by that time a modified order comes, well, in this case the validation process is going to scream and say that I cannot find order number 1, 2, 3, 4 in the order book, so this order is not valid. And that is going to create a bug called a lag bug or a Mendel bug, which needs to be accounted for. Well, this happened because of a very stupid definition of split and not taking care of transaction boundaries. If you think about it, a very simple change that needs to be done to take care of this is that move the step number 3 to the validation process. That means you take the 1, 2 and 3 as one transaction. Only if it is written to the order book is the transaction complete. And once that is done, then any number of order modifications can be taken care of because order details are present. You've completely separated the lag in the matching versus the details that need to be written for the order. So this, in hindsight, is a simple bug fix. But thinking about it, when you have a system in maintenance where the code has not been touched for 15 and 20 years, nobody really thinks about a simple change that can cause havoc. So better make sure when you do performance optimizations, you really thought about all the changes and what kind of impact they can have. And that's why a lot of things have to be analyzed, even though it appears like a very simple change. Now let's get on to performance controls as we spoke about them. And as we said, we want controls that will last for years. And what kind of architecture invariants can we have because of these controls? So let's take an example. In the large stock exchange, initially this had human traders. This still has a lot of internet and human traders. So let's initially focus on human traders. That whenever a stock price changes, an event triggers the change. It could be because of orders, it could be because of trades, and whenever a trade happens, the price has to be broadcast to the market. So these events keep occurring of new orders and trades coming into the system, and the market needs to know what is the latest price of a given stock. Now if you are having events which are in excess of 100 trades a second, and you want these events to be broadcast to trader workstations, you have to keep in mind is that this is going to be a pretty difficult thing to keep optimizing. Today you have 100 trades a second, tomorrow this will grow to 200 trades a second, day after tomorrow it will grow to 500 trades per second, in the future it goes to 1000 trades per second, then 10,000 trades per second. So you have to constantly engineer this as your volumes increase, as your rates increase, and that's going to be more and more difficult. So instead of that, why not take a step back and really look at it, that who are seeing these trades? They are just human traders. Can the human eye detect events faster than 100 per second? In fact, it's going to be much less. So if you look at the human eye, it has something called persistence of vision, wherein you can detect change 10 times per second. So if you can detect at this rate, why do you need to send data that fast? So that simple change was implemented in the stock exchange to look at what's called a timer driven broadcast. So essentially, several years back when it was analyzed, it was found that 50% of trades occur in the top 5 securities, 90% in the top 30. Well, that was at a given point in time. These numbers could keep changing. So the idea was, why not have a segregation into hot securities and cold securities and have different timer values for these, so that the human eye cannot find out the change, and you're still quite comfortable that even if the actual changes occur at thousands per second, you may broadcast it only once every few seconds. Essentially, the idea is to make it a configurable option where you have k sets of securities, each with different timer values, and have these timer values changed as time progresses depending on the market requirements. So if, for example, you're dealing with program trading, which is very prevalent right now, you change the timer values to microseconds. If you have a large number of human traders, then keep the timer value in the range of hundreds of milliseconds or seconds, depending on how comfortable the traders are, who are the type of traders that you're dealing with. So in this case, as you see, this particular control which was provided at the application level has actually lasted for more than a decade without any change, without any significant worry about bandwidth increase and computation increase as time progressed, because all that was done was just keep this architectural control provided to the end user and use it as an architectural option which has a parameter that can be controlled. There is no need of very sophisticated kind of engineering, because you're totally looking at a set of stocks which are in the range of a few thousands, and all this data can easily be kept in memory for the latest stock prices. Of course, there may be increase in number of stocks, and you may also look at a second level of engineering, that how do I deal with network optimizations. So essentially, whenever you deal with an application packet of broadcast data, you need to set the best prices for n stocks in one application packet. You can use compression using, let's say, Lempel-Ziv Oberhummer, that's LZO, which comes as a freeware, and that gives you a good deal of compression, easily about 3x for many kinds of applications which have small packets. Now these packets are available, but you've taken, without compression, applied LZO, and you get packets of different sizes. Now you need to take these packets and pack them into fixed size message frames that are actually broadcast out. So how would you go about taking a number of compressed packets, fit them into fixed size message frames, and your target now is to minimize the number of frames that need to go out. So this is analogous to you going on vacation and you have a number of objects to pack. You want to minimize the number of bags that you carry. Now what would be the algorithm that you would use for packing? Well, you can use something as simple as first come first serve, but that will not be optimal. As it turns out, that this is a classic computer science problem called bin packing, which is known to be NP complete. That is, there is no known polynomial time algorithm that can do the optimization for you. And that doesn't mean you should just discard the optimization. You can apply heuristics, and one good heuristic that works well is longest packet first. Now with longest packet first, you can easily get an implementation that in the average case is close to optimal. In the worst case, it will be about less than twice the optimal number of frames, but in the average case you would pretty much get a very good result. So while this heuristic was chosen, it was not implemented in the first round. What was implemented in the first round was a simple first come first serve, because it was found to be very easy to implement and maintain, because at that point in time it sufficed for the bandwidth, and you also thought about the future. As we said, don't over-engineer at a given point in time, and in cases of need felt and you want more optimization, you can always revert to longest packet first at a later point in time. So that's the whole idea about performance engineering, that never over-optimize if it is not really required.